which we write symbolically using this notation. So we put A and B next to each other inside a 2x2 table, and we put these vertical bars, and that means the determinant of these numbers, it means this guy times this guy minus this guy times this guy. Okay? So that's called the determinant. And geometrically, what it measures is the area, well, not of a triangle because we didn't divide by 2, but of a parallelogram formed by A and B. So it measures the area of the parallelogram with sides A and B. And of course, if you want the triangle, then you will just divide by 2. Okay, the triangle is half the parallelogram. There's one small catch. The area usually is something that's going to be positive. This guy here has no reason to be positive or negative because, in fact, well, if you compute things, you will see that whether it's positive or negative depends on whether A and B are clockwise or counterclockwise from each other. I mean, the issue that we have, well, when we say the area is 1/2 length A, length B sine theta, that was assuming that theta is positive, that its sign is positive. Otherwise, if theta is negative, maybe we need actually to take the absolute value of this. So, just to be more truthful, I will say the determinant is either plus or minus the area. Okay. Any questions about this? Yes?
You're discussing dot product what exactly?
Oh, sorry, that's not a dot product, that's a usual multiplication. Okay? That's length A times length B times sine theta. And so that's equal to the area of a parallelogram. So let me explain that again. So if I have two vectors A and B, so I can form a parallelogram with them, or I can form a triangle. Okay? And so the area of a parallelogram is equal to length A, length B, sine theta, is equal to the determinant of A and B. While the area of a triangle is 1/2 of that. And again, to be truthful, I should say these things can be positive or negative. So depending on whether you count the angle positively or negatively, you will get either the area or minus the area. The area is actually the absolute value of these quantities. Okay, is that clearer? Okay. Yes, sorry. So if you want to compute the area, you will just take the absolute value of the determinant. Okay? So area will be well, I should say the area of the parallelogram, so that it's completely clear. Sorry, you have also a question? Explain again, sorry, what's the question? How the determinant equals the area of a parallelogram? Okay, so the area of a parallelogram, it's going to be the base times the height, right? So the base, let's take this guy to be the base, so the length of the base will be length of A. Then the height will be obtained by taking B, but only looking at the vertical part. So that will be length of B times the sine of theta. Okay, so that's how I got that the area of a parallelogram is length A, length B, sine theta. And then I did this manipulation and this trick of rotating to find a nice formula. Yes? So you're asking ahead of what I'm going to do in a few minutes. So you're asking about the magnitude of A cross B. So we're going to learn about cross product in a few minutes. And the answer is yes, but cross product is for vectors in space. Here I was simplifying things by doing things just in the plane. Okay, so just bear with me for 5 more minutes and we'll do things in space. Yes? That's correct. The way you compute this in practice is you just do this. Okay? That's how you compute a determinant. Yes? What about? So 3 dimensions we are going to do now. Okay? More questions? Should we move to... Okay, let's move to space. So there's 2 things we can do in space. And, you know, you can look for the volume of solids or you can look for the area of surfaces. So let me start with the easier of the 2. Let me start with volumes of solids. And we'll go back to area, I promise. So I claim that there's also a notion of determinant in space, and that's going to tell us how to find volumes. So let's say that we have 3 vectors, A, B, and C. And then the definition of their determinant is going to be, so the notation for that in terms of the components is the same as over there. We put the components of A, the components of B, and the components of C inside vertical bars. Okay? And of course I have to give a meaning to this. So this will be a number. And what is that number? Well, the definition I will take is that this is A1 times the determinant of what I get by looking in this lower right corner. So the 2 by 2 determinant, B2, B3, C2, C3. Then I will subtract A2 times the determinant of B1, B3, C1, C3. And then I will add A3 times the determinant B1, B2, C1, C2. And each of these guys means, again, you take B2 times C3 minus C2 times B3. And this times that minus this times that, and so on. So in fact, there's a total of 6 terms in here. Okay, and maybe some of you have already seen a different formula for 3 by 3 determinants where you directly have the 6 terms. It's the same. Okay, it's the same definition. So how to remember the structure of this formula? Well, this is called an expansion according to the first row. So we're going to take the entries in the first row, A1, A2, A3, and for each of them, we get a term. Namely, we multiply it by a 2 by 2 determinant that we get by deleting the first row and the column where we are.